Yeah.
Okay. 10 minutes. So things start working. The funny thing is that Apple wants to make self-driving car. Good luck with this high technology. So I recommend them to stay at the Mac and don't drop the ball after that. Otherwise, we're gonna get more killing. I mean, Tesla already killed one last night. All right. So welcome back from spring break. So we are going to continue um, our discussion on variational inference. So the focus of today will be scalability and how we can scale this kind of algorithm for a large amount of data. And hopefully I'll put some seed today on connection between this kind of idea and related to optimization. Hopefully next time that we talked about connection between this idea and deep learning, you can use some of the discussion that we had today. So if you remember, the idea of a variational inference was that you wanted to compute some sort of true posterior that you didn't have access to. But instead of, because we couldn't compute it, either it was computationally expensive or we didn't know how the exact form of that was, we decided to do approximation of the variational inference and limit ourselves with a family that are quote-unquote easy, so easy in terms of computation, and search within that family and minimize some sort of a distance between that a member of that family and our posterior. So that was the general idea of the variational inference that cast the computation of this posterior that we were interested in to an optimization problem. But then we mentioned that it's, well, like if we knew that posterior, we didn't need to find something else to be close to that, so it had some sort of like a chicken and egg problem. But then we realized that if we use a KL distance, so we can expand this term. So the KL can be written as expectation of, so if you remember, this is an expectation of log of the Q and PZ of D. And then we mentioned that, so let me put the log outside. So we can expand this. And then we realized that using a Bayes rule, I can write this as the numerator versus denominator, but because log of D, which is evidence, gets out of the expectation because it's not it is not dependent on Z. And then suddenly we have a term we can optimize because if we are given a graphical model, we can write the joint likelihood. That is easy most of the time. And although we cannot compute this exactly because we don't have access to this is actually what we want to compute, we can compute this part, and this is a constant. And we said that the negative of this term is called evidence lower bound. And we maximizing this, which is basically negative of these terms, equivalent of minimizing this, which is equivalent of minimizing this distance. So we have this graph that this was what we wanted to compute. Because we didn't have access to this, we tried to maximize the ELBO, which minimized the distance. That was the general idea of variational inference idea. Any idea about this? We're going to build on the top of that further today. Any question? Nope. Okay. So then we mentioned that there are several different interpretations for evidence lower bound of ELBO. So one would be, so remember we want to maximize the ELBO. So one is that, well, assuming that Y is your data and the Q is the set of posterior family of the posterior approximation, the first term can be viewed as a reconstruction error. So you want to find a Q that maximizes your likelihood, and while at the same time is not too far from your prior, right? So this was your prior, and you don't want them to be that far. So remember, you're maximizing this, so you can view this as minimizing the negative of that, so which is basically you can view this term as a regularizer to the reconstruction error. So we more or less stopped last time at the point that, okay, so this is just a view, how we can actually go and optimize this, because if we want to view it as an optimization over a set of functions, we haven't achieved anything computationally because that problem is as hard as the original problem. So we resort to a family of parametric method. We started with the idea of a mean field approximation that assumes that the Q, which is parameterized, this is the family that tries to approximate the posterior that we want, and it's parameterized by phi. We assume that, we mentioned that the naive mean field, or the vanilla version of the mean field, assumes that Q is fully factorizable. So it can be, so if X is, I don't know, like say 10 dimension, this is going to be multiplication of the 10 terms. I have to say that doesn't have to be factorized over each of the items, can be factorized over the block. Depends on the problem. And we see some examples today. So what is that equivalent to? So it is equivalent of having this assumption that, for example, if I have a Markov random field, the square represents the pairwise potential and or the factors, unitary or binary factors. So this is equivalent of approximating the posterior with cutting all of the pairwise terms. So that was the idea of naive mean field. All right, so we also worked out that what are the update rules look like for the mean field. This is still from the last session. We said that, okay, so if you remember, the idea of mean field is that I write the entire approximate posterior Q x phi as a multiplication of the bunch of terms is fully factorizable. So let's fix all of them the same, optimize only Qj. Or basically, I'm saying that parameters of the Qj, but I can write it as a shorthand, just Qj. So if I want to expand that, so remember, I use this notation as P, Z, and D join, and and basically, I mean, at the end, I'm interested to computing this posterior, but this posterior is basically PZ, DPD. So I can say that this PZD is proportional to PZD. So as if I know PZ up to a normalization, but the computing that normalization was hard. So here what I'm writing as P tilde is assume that you want to compute PX, but you don't have normalizer, but you can evaluate it, assuming that the normalization is factored out. So let's say that I only focus on one of them, one of the terms in the factorization, which is Qj. So if I expand that, so I'm going to get, this is still from the last session, so I'm going to have terms look like this. So it's basically what I did was that I want to focus on one of the Qj's. So I bring, if you remember, I bring one of the Qj's out and rewrote the entire, they have received 1 million message. So I can write it as a maximization that like one of the Qj's comes out. And then I'm going to have terms look like this, that the first term was as if I'm pushing the expectation with respect to the rest of the term, getting rid of all the rest of the Qj's, which looks like this term. So this is expectation with respect to the rest of the Q's of this term. And the second term is what? What is this thing? Is there? Entropy, right? So if I fix all of the Q's and focus on one of them, in each step of the optimization is as if I am taking expectation of unnormalized posterior with respect to rest of the queues, and then adding an entropy to this as a regularizer. So that was what it boils down to. So every update, in every step of the update, I have to do step like this. And hopefully, if you remember it from last time, we said that, okay, so if we make a derivative, variational derivative with respect to qj and set it to 0, I'm going to end up with the terms like this, that if you remember, the derivative of the variational derivative of this term was qj, and variational derivative of this is just this expectation, which is the inside term. So if I set it to 0, I'm going to have an update rules that look like that. So always take an expectation with the rest of the variables of the log of the unnormalized posterior, and exponentiate it and find a normalizer. That's it. This is how my normalization, this is how my mean field update looks like. So you want to compute the update with respect to jth element, compute the expectation of the log of the queues with respect to rest of the variables, which I'm going to show you an examples, exponentiate and normalize. This is how the update rules look like. So this is still from the last time. Is there any question? Because you're going to see this update rule quite a lot. So you can view this as a fixed point iteration. So if I have Q blocks, so assume that this is Q1, this is, let's say, QK. I take an expectation with respect to the rest of them, update the parameters of this one, and then go to this term, take expectation with respect to this guy, exponentiate, update, and go on. That's how if you want to write the mean field optimization, this is how it looks like. Any question? Yes.
What was J and QJs again?
So if you remember from this, okay, so this is the QJ. So here I wrote this QI. It's basically the same thing. So I am assuming that in the context of a naive mean field, I can write it as a fully factorizable form. And I'm trying to, so this is like Q1 multiplied by Q2, so on and so forth. I'm trying to update one of them, one element at a time. Okay, so let's do case, yes?
Under what conditions does this converge?
Okay, that's a really good question. So this is exactly equivalent of maximizing the ELBO. So we know that in every step, I am increasing the ELBO. So this is basically, you don't have the proof of going to basically global optimum, but you know that it converges. Because in every step, you're reducing the cost function or maximizing the ELBO.
And do we know how many steps are required depending on what Q functions we choose? Like what classes we're searching over?
Are you talking about in the context of regret type of like a regret bound or no? So the way that so let me give you a practical answer and then you can go a little bit. So the practical answer to that is that the general idea is like this. Let's say that you have k terms, you update each of these terms, and because you know that in every update your cost function is increasing, you basically stop whenever the terms does not change that much. So you can also monitor the ELBO. So it usually goes up and plateau, and you stop whenever it doesn't change that much. Either your stopping rule can be your update of the parameters, or you just monitor the ELBO in saturate. So this is the, I think, like 99.9% of the practice. If you ask me, how does it behave with respect to different choices of the queue? Okay. So I'm going to give you one example in the following. So if you're using a conjugate, which means that in your hierarchical model, these are conjugate, which means that, as I'm going to show you, every update is closed form. So it's not really like there's not that much to do in terms of like optimizations. Like you just work out the examples. So, and if the entire model is conjugate, and you know the posterior lives in the same, because of the conjugacy between prior and the likelihood, you know that the posterior is the same for, you just update it. So there is no, so because you know that it lives in the same family, you don't have that much of choice in terms of which family you choose from, because you know that it's the same family. So there is no reason to go for a different family. So that, but that is your design. So you design your model to have a conjugate structure. So if you decided not to go for the conjugate, which means that your optimization won't be closed form, then you have a lot of room to wiggle. Design choices how I can form the approximate the cube. I'm not going to cover it today. Maybe so I'll definitely talk about it in the deep learning section. So then there is a computation. So there is a balance between how flexible my class would be versus how much I can do the computation in a feasible way. So then, I would say, because you don't have a closed form for your form of approximate posterior, you have to think about like how much you are willing to pay computationally. So your computational costs decide, and so of course what you want to compute from it decides what family you choose. Did I answer the question?
Yes.
Okay. All right. So let's start with a case study, our favorite case study model during the class, Latent Dirichlet allocation. Hopefully you guys remember how it looks like. This is the plate model of the LDA. So remember LDA was we're using for topic modeling. XMN represent the words. So we have M documents, and within each document we have N M words, right? So these X and N are 100 representation of the words, and theta D was what? So can somebody tell me what is phi? It's fine to be wrong. It's a topic modeling, right? So something should be topic.
Topic,
Huh?
the topic prior.
So phi k are the topics, right? Distribution of the word in k topics. And theta m was, what is that?
Topic distribution.
Yes, exactly. Distribution of the topics for document m. Right. And what is ZNN? MN? Topic of each word, exactly. So this was the distribution. This was basically the structure of our topic modeling. We discussed it last time. So phi k was the topic, which was because the distribution is you can model it with the Dirichlet with the parameter beta, and theta m was a proportion of the topics for each document, which has a parameter alpha, and Zm was a latent variable that tags the words that which topic is coming from, and Xm is observed by. Now, you want to integrate all of these latent variables out, and the exact inference was not possible because it's expensive. By the way, can somebody tell me why is it expensive? Any idea why is it expensive? Two separate what?
Not two separate hierarchical.
Right. So can you elaborate? That's a right. So can you elaborate a little bit more on that?
Yeah. So for each document, you need to draw a topic distribution, and within the document, you draw the words from that distribution draw from the topic.
Right. So you see some sort of the V structure here, right? Because you see some V structure, so these Zm and phi k's are dependent on each other. So if you want to write the joint distribution, this becomes dependent. And if you want to do exact inference, you have lots of words, and you have very high dimensional distribution, and everything is intertwined. So If you want to do exact inference, good luck with that. So we have to do an approximate inference. Yes, any question? No, sorry. All right, so going back to our exact inference, so I'm going to write the joint distribution. I just wrote dot because there are lots of variables. If I write all of them, the formulation goes to the other side of the screen. So this by dot here, I'm saying that joint distribution of all of the variables. So you can easily read it from the graphical model, right? The prior of the topic proportion, the words, distribution of the words, label of the words, and the topics, right? This is, I'm just writing the joint distribution. So the latent variables are these three guys, these three blocks. Now, I'm interested in computing posterior, so it's intractable, so I'm going to do approximation. So the approximation, I'm going to use mean field. So the Q here, by here, I'm saying that Q, all of the phi's, all of the z's, and all of the thetas. Yeah, that's what I mean by this. So remember the idea of the mean field was to write it as a fully factorizable form. But as I told you, you don't have to go over single variables. You can go over block of the variable. So the block of the variable would be this block, and this block. So we have K of this block. We have M of this block, and M multiplied by M of this block. Right? So this is what I mean by fully factorizable form. Is the setup clear? Okay. So now let's derive the update rules for that. So what is the main thing that we have to remember? This update rule that I showed you earlier. That when you want to update one of these blocks, you take an expectation with respect to the rest of them. You take an expectation of the log of the joint distribution, exponential and normalize. So you may say that, well, okay, so I might be able to take this expectation, and exponentiation is easy. Is it easy to compute this normalization? Because we know that for a general form, we cannot compute this normalization. If we would, we wouldn't need to compute the approximate posterior. Just write the joint likelihood and normalize it. That's our posterior. So now I'm going to give you an example that in this class of the graphical model, because of the conjugacy assumption that we have, all of these are closed form. We can compute it very quickly. So let's start. So how can I update Q? Q of theta m. I have to take expectation with respect to phi's and zm's. So I have to compute expectation with all of the qm, zm's. And so, and it is only, so why there is no phi k here?
Because it's deseparated.
Yes.
X is observed.
Yes. So if I take an expectation with respect to z, as if I know z's, it blocks it from the phi. So I can only take I only need to take an expectation with respect to zm's. And let's extend what you said. What's your name? Chirag. Okay. So I only need to take an expectation with respect to zm of the same document, right? I don't need to care about the other documents, right? That's because the same idea. Make sense? Okay. So, but this is easy to compute. Why is it easy to compute? So remember in LDA, we assumed that phi m was Dirichlet, right? So this was Dirichlet, and this was Dirichlet. So hopefully you guys remember the form of the Dirichlet. So the form of the Dirichlet was, so has the following form, that the log of the pi k, alpha k minus 1, exponentiated with some normalization, right? And also the categorical distribution had a similar form. So if you remember, the categorical distribution was looked like something like this. P Zn equal to K. Right? Okay. So now, what is nice about these two is that when I just substitute these two terms inside of the term on the top, and I get the form that looks like this. So what is interesting about it is that, remember our prior looked like this, and my posterior looks like that. And they all share the same form. So there is a log of the pi nm, or mk, and there is another term. So you can easily see that q theta m is what distribution? This was Dirichlet, and it ended up to the same form. What should the posterior should be? Has the same form, right? It's only, instead of alpha k minus 1, it has alpha k minus 1 plus another term, which is basically, with respect to theta m, is a constant, right? So what does it mean about the posterior? Which family it should be? So remember our prior, this is the density of theta m, right? So it has a log of the pi mk and the parameter of the prior. So these looks like the same. These two looks like the same. Looks the same, right? Except that this constant is updated with another constant. So if I complete this distribution and find the normalization of the prior and posterior should have the same form. Yes.
My question is a bit relevant to upper equation.
Yeah.
Why again that five k's are out of the equation?
So you're computing the posterior of this guy, right?
Okay.
If I make an expectation with respect to this, right? That's if I know it. There is no path from here to go there. It blocks the path. Remember the baseball algorithm? So if I fix this, I cannot pass through. Right?
Yeah, but that would only make sense if you condition on it during your
So you're taking expectation. So you're taking expectation means that you're taking expectation of a function. P, Z, basically here is Q. Q, Z, N. I'm substituting, what do I do in expectation? The expectation is like a sum, right? A sample from it and just plug that in. So guys, you want to see. If you actually work that out, you see that all of these terms that depend on phi gets out of it because there is no joint term between phi k and theta m. There is no joint term. But another way of saying that is like taking this expectation blocks them away from each other. Oh, another thing. The form of the Q was fully factorizable. Right? Okay. So when it is fully factorizable, it's like Q of the phi's multiplied by Q of the z's multiplied by Q of the theta. So when you are taking expectation, it's like take expectation with respect to first guy, second guy, third guy. So right. So I can write an expectation of P, X, Y, Z if they are independent of some function of X, Y, Z. I can write it as expectation of the X, expectation of the Y, expectation of the Z of that function.
You can always do that. That's law of total probability.
No. Law of the total probability has a conditional.
Okay.
If they are independent, I can write it like that. Okay, so any other question? All right. So it boils down that so I can read. So the posterior is a Dirichlet, but it's expected because the structure of our model was conjugate. So remember the conjugate? I guess like we discussed it when we were talking about generalized linear model. So if X is categorical distribution, and our phi's are coming from Dirichlet distribution. Because these guys are conjugate of each other, posterior would have the same form. And because we had this assumption in LDA, our posterior comes at the same form. Why is it important? Because if you guys remember, computing the normalizer in general is not easy, but if you see the posterior has the same form, you can easily complete it because it has the same form. And so this is basically idea of, this is one of the reasons that we love conjugacy so much, because we know that we can easily complete the posterior. We can compute it as a close one. So, but you may think that, well, this was too specific example. Can I generalize it? So let's redraw this model again. So I'm going to expand some of this plate model. So I'm going to rewrite this again in the following form. So all I did here was that I removed this plate and then repeated that block again, right? Is that clear what I did? Okay. And so, and again, so there should be a phi k going through each of these x's, right? This is, I just get rid of the plate and repeated that words again. This is just redrawing the same thing. But hopefully you see some sort of like a structure here. There are set of the variables. So here, the unit of our observation is a document. There are set of variables that repeated with our observation, that here is document, and set of the variables that does not. So if I have, let's say, 1,000 documents, these blocks get repeated, but this stays k. So the general idea is that these are, for many of the graphical models that we deal with, we have set of the variables that gets repeated with the data, and set of the variables that are shared across all of them. So the one that are repeated with the data, we call it local variables, and the one that are shared across the samples, we call it global. And for many of the graphical, for many of the models that we deal with, we have models like that. So in this case, I just redraw everything, and here by Zn I mean basically concatenation of these these latent random variables that previously I call it theta n, and all of this block, just to save the notation. And by beta, I'm talking about this. So for many graphical models that we deal with, we have a structure that looks like that. We set of the random variables that get repeated with the data and something that is shared. So the beta we refer to as global, and the Zm, which is concatenation of all of the things that are local as a local random variables. So a few observations is that the same thing that you mentioned earlier is that if I write the joint distribution of x, y, z's, which has a very straightforward form that I'm showing at the top, if I condition on the rest of the random variables, what do you expect at the end of it? So by x minus n, z minus n, I'm talking about, let's assume that all of the random variables are observed. All of the rest of let's say here, the rest of the documents are observed. What do you expect from that? So what that should be equal to? So I'm conditioning on beta. I'm assuming that alpha is also, this is a parameter here is known. So if I condition, so for x, n, and zn, if I condition on the rest of it, what should that be equal to?
So beta and alpha would be independent of x.
Say it again.
So beta and alpha would be independent of x minus n and z minus n. So that we can separate them out. We don't have to multiply all of them.
Yeah, so it's basically you are saying that if I know beta and alpha, I don't need the rest of it, right? So I can write this as this. So conditioning on the rest, I can get rid of this. Because beta is basically blocks them from the rest of the variables. And this is very useful. So let's make further assumption. Let's assume that we are using conjugate model, the same things that we did as the Latent Dirichlet allocation. And let's say that we are limiting ourselves to the exponential family for the time being. So that means that our P of the beta is, what was this called? Base measure. Base measure. And what is this? Sufficient statistic and natural parameters. And this, normalize, log partition function. Okay, so I'm assuming that each of these are coming from exponential family. Don't get caught up into the ugly notation that I have, because I have to say that it's coming from exponential family. This looks like exponential family. Because the sufficient statistics only depends on the random variables, and the rest of the variables goes to this. That's what this ugly notation looks like. But I have to write it to write it for you to be correct. All right. So, and again, the general form of that, I cannot compute the exact form of the posterior, so I'm going to resort to mean field. So the general idea of the mean field would be factorization of the global and set of local random variables, right? And again, I'm assuming that my form of posteriors, remember, we are assuming the conjugacy, which means that our posterior would be the same family, so I can easily assume that, first of all, they are coming from exponential family. They stay also in the same family, which means that it's easy to choose the form of the Q betas and the QZs because of the conjugacy. Yes.
I don't understand why, if you everything is conjugate to each other, why exact inferences is still a problem.
So that doesn't solve your problem. So you're assuming conjugacy means that you're okay. So when you're assuming conjugacy in a generalized linear model, so that's for one conditional, things are easy, right? So remember, when you're solving this problem, right? This is observed, this is latent. Because of the conjugacy, if you had the prior over Py, your posterior Y condition on Y condition on X was in the same family. The general form, so what you're saying about the conjugacy means that the actual posterior is not conjugate. Actual posterior is not conjugate. The conditionals, the pairwise conditional are conjugate. So if I have because of the idea of the mean field, I'm assuming the Q's that are fully factorizable. In reality, they are not. And if you want to model the reality, everything breaks apart because you cannot compute that expectation. But because you are assuming this fully factorizable, you end up with a model that looks like this. And this is why it's easy. Yes?
So if I fix one of my priors, then I get a closed form for the posterior, considering the other prior to be fixed. And then I can iteratively update my posterior, like in an EM-like step, right?
So can you repeat the question again?
So basically we have two priors here, which are both, and the fixed condition on one of them, the posterior is conjugate.
Mm-hmm.
So if I fix the value of 1 in one of the iterations and I update the posterior, and then I use that as to fix and do that iteratively in an EM-like approach, would that work?
So variational inference is in fact a form of expectation maximization. So, but there is one subtle difference. So in expectation maximization, you substitute the latent variable with its expectation. While in variational inference, you assume a form of distribution for the latent variable. That's, I would say, the major difference between EM and VEM, variational inference. So now, but here's the problem. If you don't want to just substitute the single variable, which is the expectation of EM, you have to assume a distribution for that. And the general form of the distribution for that variable that are latent are not known, and it depends on everybody because of these real structures that we have. And this is why we resort to fully factorizable, because it's based, well, it's somewhat our computational laziness. Sort of. We just can't do it in closed form. We assume this approximation that helps us to solve this problem. So to answer your question, if you're happy with the single point estimation, then EM is good. But if you care about, for example, computing some sort of variance around your related variable, then you resort either to sampling approach that we'll cover next time, or to this kind of problem, this kind of approach. All right. So remember the same rule of the variational inference. Take expectation with respect to rest of them, exponentiate, normalize. But because we have the conjugate model, computing that normalization here is easy. And so the general idea here is that we have a set of local variables which was our QZs. We first update those with the parameter of phi, and then use that to update betas. And this is basically sort of, you can view it as a pseudo-code, or yes, there's a pseudo-code for many of the variational inference that follows this form that I showed you earlier, that there is a set of variables that scales with the data, and there's a set of variables that are shared. So this is the pseudo-code for many, many different kinds of variational inference algorithm that has a conjugate model. So all you need to do is that in your own model, substitute this term and substitute this term. And computing this expectation is basically you have to go back and say, what was my assumption? How does my features, or in this case, eta g's, which are my natural parameters, look like? Let me compute this expectation with hand, or nowadays you just don't even need to do it with hand. We have many great tools that do it for us. But anyway, so you just substitute that in, and you have your update tools. So I'm going to switch the view a little bit, because what I showed you was sort of like a fixed form view towards a mean field approach. So every time you need to compute the update rule, fix one of the, so you assume that it's fully factorizable, you update each of the terms in the queues and go on. But there was a fundamental assumption that enables us to do that, and that was conjugacy. And it can be quite limiting in some of the models that you may say that, well, the reason that you are making conjugate assumption because you want to have a closed form in your approximate posterior, I'm not willing to make that assumption because that class of models are so limiting. Why not having a totally optimization view toward variational inference? So in the following slide, I'm going to introduce another view toward variational inference, which is fully just like viewed as an optimization problem, take a gradient and go on. So let's go back to the form of ELBO that we had at the beginning. So remember, we had first term, which was our reconstruction term, and the second term, which was a regularization term, which was trying to enforce that our posterior shouldn't be too far as a product. You can basically view the same. So here I'm going to extend my formulation a little bit by introducing theta. So I'm assuming that your model may also have a set of parameters, I call it here theta, that you may not have. So here an example of that would be, I have a hierarchical model, but part of my model has a deep learning module. And I want to find the parameters of that module. So this is an example. So theta are the parameter of your original model, and phi's are the parameters of your posterior, approximate posterior. So one way to view this problem as sort of like a decoder-encoder approach. So the encoder basically, so how many people are familiar with variational autoencoder? Okay, so we will get there given that not everybody knows about this approach, is basically, so let's say that you have a channel that you want to use to communicate with your colleague. But let's say Verizon put the limit on the bits that you want to send to your colleague, and you cannot use arbitrarily as many bits that you want. So you want to send the new video to your friend, and you have to limit yourself to the minimum number of bits, otherwise you're going to be high charging your credit card. So you need some sort of like a compression of the data and decompression of the data, right? Compress the data to minimize the amount of bit that you want to send without compromising information, and decompress it back at the destination. So one can view variational inference as the same view, in the same way that the z's, which are set of all of your latent random variables, are this code that you have, this small number of codes that compress all of your data to a lower dimensional space. And your posterior gets that code and decompress it back to reconstruct it. So one can view the first step, which was the reconstruction, as the data code length, and the other part as a hypothesis step, as a hypothesis code. So one way to view that is that you are generating Z. You have the Z that passes through your likelihood model to reconstruct your Y. That's your decoder. And your encoder gets the data and constructs a smaller number of the information that you can use to send it through the channel. This is basically, I'm not adding any math to this. I'm just trying to put a different way of viewing this kind of optimization, these kind of problems through, from information theory point of view. So what is that useful? So let's say that, first of all, you don't know what kind of coding. You want your coder has some knob to tune, and these are the thetas are the parameters of your decoding, and phi. So this is the parameter of the encoder. This is the parameter of the decoder. Right? And it depends on the data. So if you want to send, let's say, a letter, that coding would be very different than if you want to send a video, right? If you want to send a letter, the encoder can be, I have a dictionary, I just count the number of words, and that's what I send, right? But if I want to send a video, you may want to use the smoothness on the image, computing to block and things like that. So these decoder are dependent on the data. Is that clear? Okay. So why do we care about this? Because remember here that even your model has a parameter theta that you don't know, and your posterior has a parameter that you don't know, and you want to find both of them at the same time. So one can say that at the end of the day, I want to optimize that guy at the top. Why not taking gradient with respect to phi and taking gradient with respect to theta? Just run it, right? I can do that, right? So it would be, it's going to have basically two modules. The first module, I'm going to take a gradient with respect to phi, which is the parameter of my approximate posterior. And so you can view it as an ES step. And in the MS step, you are maximizing the parameter of your model. So it's like, this is basically the EM view that you just mentioned. So I'm updating the parameter of my model in ES step. I'm updating parameter of my approximate posterior in MS step. It's very similar fashion as expectation maximization. Is the setup clear now? Okay, so I'm going to show you. This is basically the gist. If you want to view it as a optimization problem, that's how it looks like. But now you should be able to compute this gradient, right? So now we know how to estimate this. If you have a model, your likelihood model, all you need to do is that pass through the gradient inside of this. And, for example, use TensorFlow or PyTorch or whatever you want to pass this gradient and compute it. You can have your deep learning, your favorite deep learning module inside of it, doesn't really matter. It's just, you just have to compute this expectation. So computing this gradient is easy. And you can compute this expectation. How can I compute this expectation? So I managed to, so this is, let's say, my model that can even include my, let's say, deep learning as a sub-module. Computing this gradient is, I can use any of these off-the-shelf packages that can compute the expectation. They compute the gradient. Now I left off with computing this expectation. So how can I do that? What is the first thing you would do? Exactly. You sample from Q, substitute that in, an average. So this is easy. What about the one on the top? Can I do the same? Why not?
You have to compute the gradient
You compute gradient of what?
with respect to the parameters. So
Exactly. So if you want to do that, you want to compute the gradient with respect to phi, and you are taking expectation with respect to q phi. So I have to do something for that. So let's see what we can do. So the problem here is that we want to so remember. So I'm going to focus on one of these terms because the other one follows the same procedure. So I'm going to focus on the first term. So I want to take a gradient with respect to phi of this term, right? This term on the top. Yes.
One question is, isn't sampling from Q phi expensive because you have to consider all the possible configurations?
No, because you are assuming that, so let's start with mean field, right? If you are doing mean field, you're assuming that it's fully factorizable. So you can basically sample from each of the modules, substitute them. So that's not hard. Even if it is they are dependent, as long as you can do the sampling, you're fine. All right. So instead of this, I'm going to write it as a general model. So I want to compute the gradient of the phi of some function of the z, right? And here in this case, f is log of pz, but it doesn't matter. So if I work it out for this example on the right, I'm fine, right? So let's work that out. So if I want to compute that, so this is fz q phi z, right? Easy. If I bring the gradient inside, I'm going to get gradient of phi qz dz. Okay? Now the problem here is that I cannot write this as an expectation. Help me to write this as an expectation.
you can divide by Q.
Okay, so great. So let's do that. So let's multiply it by phi and divide it by that, right? I haven't done anything here, right? So now I can write this as an expectation of this block. So can somebody tell me that what this is? So it's a gradient of the log of the q phi z. Right? So I managed to write this expectation. I managed to write this gradient as an expectation. Now I can do that trick. That sample from qz, substitute that in, and continue. So that is a trick that we use to compute that expectation with respect to phi. But now we have to deal with another issue, that although we can sample from Q and substitute that in as an estimate of the Qs, this is a Monte Carlo approximation of the expectation. And if we always were able to do that, like the life was rosy. So what's the issue with this kind of approximation?
I just have a quick question.
Sure.
Do you take a gradient numerically?
Oh no, so you don't have to take a gradient numerically.
Okay.
So I'm assuming that you can compute this
explicitly.
explicitly.
And then just substitute.
Exactly. So many of the models that we have,
Yeah.
even so we substitute this with PyTorch. Okay. So now we have to deal with another problem that we have to compute this expectation. We are sampling from QZ, substitute that in and average. What can happen? What can go wrong? I said if you remember, I said many of the inference algorithms this way or the other can be written as an expectation, right?
Your sample does not represent the true population.
Yeah, but let's assume that might not be the correct posterior, but let's say for a time being it's an approximate posterior. I'm happy with this. But what is the general problem of substituting actual expectation with empirical expectation?
In a high-dimensional case, it's not a very good approximation.
Why is that? That's correct. Why?
Because
How do you think?
there are points that like you might have actually your function value might be very high, but your density might be very low. So if you don't pick any sample from those points, you actually underestimate the expectation.
So it's a variance problem, right?
Yes.
So my estimation is a correct estimation, is a consistent estimation unbiased, but it may have a terrible variance. And it becomes worse and worse as the dimensionality increases. So if I do something like that, so here I'm showing you plot from the Miller's paper. And the x-axis is the wall clock, and the y-axis is showing the ELBO, and of course, maximizing ELBO should look like this. And I'm showing you the result of approximating that expectation with 2 samples, 10 samples, and 50 samples, right? And you see that the 2 samples, ELBO is not either is behaving funny, or it gets stuck in the local minimum, and as you see that as I increase the number of the samples, first of all, 2 samples are not enough. It has a high variance, and it doesn't achieve the values it can possibly achieve with the higher samples. And you see that 2 samples perform worse than 10 samples, and that perform worse than 50 samples, right? But the problem is that if you draw a lot of samples and substitute that in, your algorithm becomes expensive. In every iteration, you have to draw lots of samples, an average, and do this to get a high quality results. So the next step would be, all right, we managed to write the general optimization. We managed to compute the gradient. Now we have to control the variance. So the idea of the so yeah, I can still do it. So the idea of the control variance is that you want to introduce another random variable that you know it's mean and has a correlation with what you want to estimate, so that it has reduced the variance. So let me show you an example. So let's say that you want to compute an expectation of g hat, which is g. So you're going to introduce another random variable, which is g tilde, that you're for whatever reason, you know that it's closed form, right? So you know it's mean closed form. And you're going to introduce new random variable, which is, I'm going to call it the g plus control variant. And the new variable is going to be g tilde minus m. So remember, I know so this is basically an expectation of the g tilde. So this is the g tilde and the expectation of the g tilde. And this is what you want to optimize, what you want to compute the expectation of. So the cool things about this is that these two variables have the same expectation, right? It's for very obvious reason, because if you take an expectation of this term is 0, so the control variant and g tilde that you are interested in has the same expectation. But the good things about GCV is that it has a lower variance. And the reason is that, So if I write it as an expectation, if I write the variance of the GCV, it's going to be variance of this guy versus variance of that guy. And if I write it down, I'm going to get the same, I'm going to have the following form. So now I have the free parameter C. If I take a gradient of the C and set it to 0, so I'm going to get the form that looks like the cross correlation between G hat and G tilde. Remember, G hat was what we are interested in. G tilde was our control variance. And it's going to be variance of the G tilde. If I write the variance of the control variant, it's going to have 1 minus correlation of the VG. And because rho is between 0 and 1 is the correlation, the GCV is going to have a lower variance than this. So now your catch, I'll get back to it. The catch would be, how can I find another random variable that has a correlation with what I want to estimate, and I know its mean, and then the rest just follows. Yes?
So how do you calculate the covariance there if you are not even able to calculate the expectation?
No. So what I'm saying here is that you don't have to compute the covariance. You don't have to. This is basically my analysis to show that this. So because I have to prove to you that this has a lower variance, right? So I'm saying that it doesn't introduce any bias because I just subtract its mean. I want to show you that it has a lower variance. It has some covariance. I don't care what it is. Okay. All I did was that I put the C to some cross correlation. So you may say that to set that C, you have to know the cross covariance. But all I can say is that if I put it approximately to that value, I'm getting lower variance. So the literature of the controlling variance is actually pretty big, and there are lots of, well, relatively, and there are lots of choices what I can choose between G and M, and what I can choose C bar and C, and I'm not going to go through that, but I want to give you the general idea why introducing another random variable that you know its mean can control the variance. This is a very simple case scenario. So what is that good for? You see the behaviors like that. You see that the behavior has improved. That if you don't use the control variance, you're going to have a dashed line. And if you control the variance, you're going to get the same, much better behavior. So the behavior of the algorithm would be equivalent of using 5 times more samples. But basically, you get this nice behavior with less computational cost if you control the variance. All right, so now going back to our optimization problem, we still have, if you want to scale it for a very large amount of data, you still have a few other challenges to deal with. One of the challenges that you have to deal with, that remember that we have this phi n, and we have to compute this gradient for all of the data. So every iteration, I have to compute this gradient and substitute all of the data. And if you have a lot of samples, this is going to be a big challenge because every time you have to look over all of the data. And similarly for this, you have to compute this summation over all of this data. So what do you think, what is the idea? How can I circumvent that challenge? Huh? Stochastic variance. So what is the idea of that?
Instead of doing it over the entire data set, do it over a small mini batch.
Yeah, exactly. And rescale the gradient, and that's all. And it works amazingly well. And in fact, empirically, it works better than the gradient. So, and this is basically the idea of the stochastic variational inference, that instead of going over all of the data, work over the entire data, it is going to introduce a little bit noise to your gradient, but that's actually fine. And it works really well. So another idea to making that scalable is to use distributed optimization. So because remember, this is the idea of this is just computing the summation. So you can subdivide the data into sub-modules and send it to different servers. And each of them can compute the gradient for a sub-batch of the data and send it to a master node to compute the summation. And this way, you are able to compute much higher quality gradient if you manage to make this communication between worker and master efficient. So this is the idea of the...
They're from here, the reference is from here, Lee Anderson's.
yes, yeah. So this is basically, I took this from Severid's course that he's talking about stochastic. So basically distributed optimization, but it's basically the same idea. So you have multiple sources, you have multiple workers, each of them work on a subset of the data, they only compute the gradient and send the gradient to the master, and the master just in a way. Yeah, please do that. And so, yeah, so as I told you, you can view each of the workers as its own parameters. They don't need to communicate with each other. All they need to communicate is the master. So it also minimizes the number of communication between. So notes from the implementation point of view. So hopefully by now you can see that some sort of like a forward-backward iteration. So this viewing that as an optimization problem allows you to basically use this forward pass and backward pass in the same idea that we use in deep learning. And of course, if your model is computable on a GPU, great, you can get an even faster faster computation by just implementing part of the forward-backward algorithm in the GPU. To summarize, we talked about variational inference. There are advantages and disadvantages. So let me start talking about disadvantages first. You can compute approximate posterior only, not the actual posterior. So if you are solving a problem that in a specific context that you are solving a problem, you care about the exact posterior, then maybe variational inference is not for you. Also, another problem in variational inference is that it underestimates the variance. So in many of the applications, we care about the variance a lot, and variational inference results in underestimation of the variance of the posterior variance of the parameters. For a general form, you have to think a little bit about your optimization approach. Nowadays, I would say it's less of the problem, given that for many of the problems we want, as long as you design your forward and backward model well, the optimization is not really an issue. On the advantages side, I have to say that it's very, very flexible. So almost all of the model, you can write this as an optimization. You can solve it. It works really fast, much faster than a sampling approach. And it's numerically stable. And you also viewing it as an optimization problem, I would say, is quite liberating because you can use GPU and CPU implementation that makes the optimization faster. I didn't talk about the model selection, but you can use the value of the ELBO as sort of like an approximation of your evidence lower bound. You can use that for model selection when you want, for example, to tune the hyperparameters or K or things like that in a number of topics. And that it works really well. From my personal experience, I strongly recommend if you want to use variational inference, use the stochastic version. It's faster, and even the stochasticity of using the parameter makes the algorithm even works better. So because before that I was talking about LBP, so it's just fair to compare mean field with LBP. So the difference between LBP and mean field is that LBP optimizes the bet energy function while mean field maximizes the ELBO, so their cost functions are different. LBP is exact when your graphical model is a tree structure, while mean field, because only focus on marginals, is not going to be exact solution. So that suggests that LBP, for if your graphical model is a tree structure, use LBP, don't use mean field, because it's just the solution would be exact. And again, because LBP focuses on pairwise and unary and binary marginals, while mean field only focuses on marginals, that suggests that LBP is more accurate. But there are major major shortcomings for LBP, the optimization of the LBP is usually harder, and both of them are overconfident. Mean field is more overconfident than LBP, but they were both have more or less similar issue. Again, if you care about the variance, use sampling approach. Another disadvantage is that another disadvantage of LBP is that it basically rewrites the optimization problem that we are interested in as a bet optimization problem, but we don't know that value of that optimization is the lower bound or upper bound of what we actually want to optimize, while in mean field, we know that it's always lower bound of the partition function. That's another advantage, that you can use mean field for model selection while you cannot use the LBP. And another big setback, I would say, for LBP is that mean field is really easy to extend for graphical models that are not just discrete random variables, for continuous and discrete, a mixture of that, while LBP is limited to the discrete random variable. So the take-home message is that if you have a graphical model that's only discrete random variables, and it has some sort of the MRFE sort of a structure, use LBP, otherwise mean field is pretty good. Okay, on that I'm going to stop right now. See you next time.